time on this one, we were looking at trying the mechanism to form these three compounds. So our first step, of course, is going to be the initiation. The most liable bond is our chlorine-chlorine bond, so that's going to initiate with either heat or light to form our two chlorine radicals. And that's always going to be our first step. And oftentimes with these, we'll be forming HCl, though that byproduct isn't always shown. But totally, that'll be forming. So once we form our radicals, because remember, a hydrogen and a carbon won't spontaneously form a radical. Hydrogen doesn't stabilize a radical very well. Once we form a radical, then we can draw our propagation steps to form those compounds shown. The first compound shown can be specified by our deprotonation, or our proton abstraction, hydrogen abstraction, with our most substituted hydrogen, because that'll lead to our most stable hydrogen carbon radical. So the sigma bond between hydrogen and carbon is going to break, forming a chlorine-hydrogen bond. And then, of course, we have to form a radical, because we have two electrons in that carbon-hydrogen bond. So this is a pretty stable radical. That would lead to a lot of our product that we see. And then, continuing with our propagation, we have CO2 present. We also have some chlorine radical present, but I don't want to show a termination right now. So we can form a carbon-chlorine bond, but again, that bond has two electrons, so we have to show the other electron as well. Yep. It's pointing that the electron is going to now be only associated with the carbon. As remember, that carbon already has that bond between carbon and hydrogen. So those electrons are associated with the carbon. One of the electron goes with the chlorine and the hydrogen. The other electron has to go somewhere. The only place it can go is on that carbon. All the other carbons have full octets already. So that forms that first product. Once we have that first product, another hydrogen abstraction can occur to form the second product, and this would be our multiple chlorinations. So technically dihalogenation. So we'll have the same type of mechanism, forming a chlorine-hydrogen bond, and then in this case, forming a primary radical. And once we form that primary radical, again, we could have a very similar step as we shown with our second chlorination. And with chlorinations, these multiple halogenations are hard to control. We can control them a little bit with heat and with the amount of CO2 we have present, but there's a lot of reactivity, so oftentimes we can have these monohalogenations. Now to form that last product, we notice we have a new bond between one molecule's carbon 1 and another molecule's carbon 2. So the only way we can do that is with a coupling type reaction. If we have this byproduct that we showed being formed earlier, here, that can come together with a molecule where we formed a radical that's primary. And we're going to really look into the regioselectivity of this reaction, especially with chlorine. Of course, we're going to form more of our tertiary radical, but with chlorine we'll learn that that primary radical can also form pretty easily. So if those two radicals form, we can form a new bond between carbon 2 of one of our molecules and carbon 1 of our other molecule, because they each have a radical. So that's a termination type reaction. And what those arrows show is the new bond between carbon 1 of one molecule and carbon 2 of the other. And that's a issue with this particular reaction, because that's a byproduct that's usually not wanted. But we can show those mechanisms for all of those. Again, notice the amount of electrons that we're showing moving, that's the amount of arrows we have to draw, because each arrow represents a movement of one electron. We're talking about radical chemistry. So before we get into the thermodynamics and reactivity of this reaction, we first have to talk about initiators and inhibitors. While our chlorine-chlorine bond is the most able to form a radical based on everything we've looked at before, it still takes energy to form that chlorine-chlorine radical. Not as much energy as it would to have homolytic cleavage between a carbon and a hydrogen, or a carbon and a carbon, because our chlorine does stabilize our radical because of its size. It's big, so it allows more room for the chlorine to have. The radical to have. So if we look at our delta H, and we can definitely use our delta H for this, our bond dissociation energies, because bond dissociation energy is measuring our homolytic cleavage, so it's directly applicable. We see our delta H is 243 kilojoules per mole. And to relate that, if we were trying to do this under heat, that would be 100 degrees of Celsius. And realistically in the lab, that's not really that useful, especially because a lot of our carbon-containing compounds will start to degrade in hundreds of degrees Celsius, which is a problem. If our carbon-containing compound is breaking down, that's not an appropriate heat. And it takes a lot of time for the light for this particular reaction. So to achieve thermal initiation at a reasonable temperature, we can use what's called a radical initiator. This is going to be a molecule that can easily form a radical at lower temperatures and with less light. We don't usually need a lot of it, because we don't want it to participate in the reaction. We just want it to form the radical so we can start our propagation process. So once we form a small amount of radical, the propagation process is usually pretty quick. So that's our goal. So what do you think we need for a radical initiator? Well, what's our bond dissociation energies measuring? Which is directly related to how easy our bond breaks. What's it related to? What can we look at? We can look at the resulting product. What's our resulting product? What do we form in this reaction? We homolytically cleave a bond and we form what? Two radicals. So what can we look at to determine how easily a bond breaks? What radical is more stable? That's what we're going to look at. Our initiators are going to form even more stable radicals than this. What contributes to stability of radicals? Resonance, size of the atom, and resonance. That's what we're looking at. And in these cases, electronegativity, not as much. So when we were talking about acidity and we're looking at the resulting negative charge, we looked a lot at electronegativity. Electronegativity can help, but remember, even though we have an electron, we still don't have a complete octet. So usually size will help stabilize these more. and resonance, having more space. In both cases, size and resonance are both doing the same thing. It's giving more space for that radical to be spread out. So that's what we're going to look at. So an ideal radical initiator has a weak bond that undergoes homolytic cleavage easily, and usually a weak bond will result when we form a really stable radical, or a more stable radical. No radical is so stable. Well, most radicals, once they form, will react pretty quickly. We'll talk a little bit about inhibitors in a second. So one of those bonds is a peroxide bond. We've talked about peroxides, we've talked about using it with HBr, and we're going to really look at that in this chapter in more detail, probably on Friday, and really delve into our HBr peroxide reaction. So peroxide is one of those bonds. Our oxygen-oxygen bond, in this case, our low delta H is coming from our stability of our radical somewhat, but it's actually coming from the fact that an oxygen-oxygen bond isn't that stable. So oxygen-oxygen bond in itself isn't a very strong bond. So our peroxides break really easily, and we'll see that we use peroxides to initiate radical reactions often. And we call that a liable bond. That bond is easy to break. It's much weaker than a chlorine-chlorine bond, so the process can be achieved at 80 degrees Celsius as opposed to hundreds of degrees Celsius. Now again, we just use the peroxide to initiate the radical. Once the radical forms, the reaction goes pretty quickly, so we don't need a lot of peroxide. We just need enough to start the radical to get a bromine radical. And we'll see that more when we talk about HBr and peroxide. Also, acyl peroxides. In this case, we have the unstable oxygen-oxygen bond, which is already not very stable, but then we also have resonance of the resulting radical. So in that case, we get an even lower bond dissociation energy because we have stability with resonance there. And those can be done at even lower temperatures. And here's our resonance structure. So oftentimes they're used as initiators. The key here is you might set up a reaction. Most of the time your reagent's 1-to-1. Maybe one reagent's in excess. These, if your main compound is in 1, this might be 0.01. It's a really small amount. You don't need a lot of your initiator for these reactions, because your initiator is not actually going to participate in your final product. It's just going to start the propagation step. So we see that. At the same time, radical inhibitors are things we need to understand. Radical inhibitors are really useful. They prevent chain processes from getting started or continuing. And oftentimes we'll call them free radical scavengers. And we'll talk a bit more later on in applying radicals and how it's applied in industry, and talk a bit about food preservatives and what they do. They're basically radical inhibitors. But in the reaction process, most of the time, either we want to prevent radicals from occurring, so we might use an inhibitor, or we want to consider what could be an inhibitor because it'll stop our propagation before we want it to. One example of that is O2, oxygen in the air, which can be a radical inhibitor because it will basically react with our radical and terminate. So what do we need for a radical inhibitor? For a radical inhibitor, we need something that will react with our radical and then take our radical out of permission. So stabilize it so much to where it won't any longer react. One example is molecular oxygen. Molecular oxygen can have this structure. Notice we have 2 radicals in molecular oxygen. So each molecule in molecular oxygen can terminate 2 radicals in our propagation step. So it reacts really readily with other radicals, and it typically destroys them. And each oxygen can destroy 2 radicals. So therefore, our radical chain won't really occur under oxygen, which is why most of the time these reactions are done after we remove oxygen and put in a inert gas like N2 or argon. Argon is the most common. Argon is a little bit more expensive. Nitrogen gas is a lot cheaper. So depending on what you need, argon is usually a bit cleaner and usually has less water present. You could dry your nitrogen gas though. You pass it through a drum tube. So usually you'll do those so oxygen won't stop the step. Because we'll have a termination occur. And this can terminate with one radical, and then it can terminate with another radical, stopping the propagation. Another example of a radical inhibitor is hydroquinone. And hydroquinone is a naturally occurring compound. And we'll talk a little bit more about hydroquinone later in biological processes briefly. But hydroquinone can stabilize the radical because after we have one hydrogen abstraction, notice our radical is transferred to our hydrogen quinone. So now this is stopped. It can't react anymore. There's no radical. And then it has another hydrogen that's easily abstracted to form this. The reason why, though, it really is an inhibitor is once we have this diradical, this molecule has a resonance structure of benzoquinone. What do you notice about benzoquinone? It's not a benzene ring, but as far as radical, there aren't any. So once this has a hydrogen abstraction with two radicals and stops the process, once this forms, it quickly forms, well, not really forms. This is the more stable structure because we have no radicals, and this can no longer contribute to the propagation. So in this case, it's stabilizing because it doesn't have a radical present. Whereas our oxygen-hydrogen bond easily goes through a radical abstraction. Other radical inhibitors, which we'll look at later with food preservatives, oftentimes will stabilize the radical because once the radical forms, something is causing sterics to avoid that radical reacting anymore. We call that persistent radicals. It's not that our radical is stable, it's that once the radical forms, it gets in an energy minimum, and it can't go forward or back. So it's not that this is super stable, it's just that it takes too much energy to go either in the forward or backwards direction. Usually because it's steric. So when we look at food preservatives, I will remind you of that. Oftentimes as well, our radical is being stabilized by multiple resonance structures where they're no longer as able to react. But a lot of times what we're looking at with preservatives is sterics. Once we form the radical, it takes too much energy to go in the forward or backwards direction, so it just persists as a radical instead of reacts. Oh, and of course, drawing in those arrows, you should be able to do this. So we have our hydrogen abstraction forming our carbon-hydrogen bond, and then our radical electron is going to be on our oxygen. Then we'll have a second hydrogen abstraction. And then you should also be able to draw your resonance arrows forming a double bond here. We're showing the formation of this double bond, this pi bond, and this pi bond each can give up an electron to form this one. Remember, we have unhybridized p orbitals that are in overlapping. And then, of course, forming this pi bond. And this one stays where it was. Though, remember, this is a benzene ring, so it has that resonance. So when we're looking at this one, number one has a very liable oxygen-oxygen bond. And oftentimes, for radical initiators, you'll see a bond between two of the same atoms that are easily be broken. For example, chlorine, chlorine, bromine, bromine. And then here, oxygen, oxygen. So you see that a lot with our radical initiators. And then, of course, it's an initiator because those radicals are going to be stabilized. So that brings down our bond association energy. But number two, won't initiate a radical very well. Once a radical's there, however, it will react with the radical easily. And once it reacts with the radical, it will form again that very stable benzoquinone that doesn't have any radicals present. So that's an inhibitor. So we've been talking about the halogenation with our chlorine. What about other halogens, and how will they react? Since we already learned that HBr and peroxide only works with HBr. But this chlorination works, how does other halogens compare? So we're going to look at the thermodynamics. We're also going to use the thermodynamics to explain our regioselectivity and our differences in selectivity between chlorine and bromine. So remember, anytime we're looking at thermodynamics, we're looking at our delta G, our Gibbs free energy. So we're looking at our entropy, our enthalpy, and our entropy term. And our delta G for the spontaneous reaction has to be negative overall. So looking at our overall reaction, we have 2 molecules we're starting with, and we finish with 2 overall molecules. So our delta S is not going to have an effect on our overall reaction, because we don't have any real big change in disorder. They're about the same. So our delta H is going to be the big thing in our overall reaction, because our delta S overall is going to be negligible. So our delta G for our overall reaction is going to be roughly equal to our delta H. So that can simplify that pretty well, since we don't have any change in our delta S. So of course we can look up bond dissociation energies, and what's going to be different when we're comparing these is our bond dissociation energies depending on which halogens we're going to use for our XX bond. And these terms can be different depending on which halogen we use, so how much energy is released. So this is just our differences for our bond dissociation energies. And remember, our bonds that are broken require energy in order to be broken, so that contributes to our positive value of delta H, whereas our red, our bonds formed, release energy that contributes to our negative value of delta H. And remember, we want our overall delta G to be negative, so that's what we're looking at. So when you calculate those, what we see is a couple of things. What's one thing that you notice right away? Do any of these halogens, will any of these halogens not be spontaneous? Which one? Iodine. Iodine has a positive delta H. So iodine's not going to be spontaneous. Which of these, of the 3 that work, fluorine, chlorine, and bromine, do you think will be most useful? You might think fluorine. That's not true. Fluorine is almost never used because it's so reactive, it's violent, it's hard to control, and it's dangerous. Just because you have a larger negative value doesn't mean it's useful. And we're going to really look at this because we're going to learn by looking at the thermodynamics that bromine is actually the best to use. Chlorine is also really hard to control, but bromine is easy to control. Think about driving. Okay, I'm driving, I'm going a good speed limit, whatever. Let's say I decide to go 200 miles an hour, and there's a rock. Is it easy to control my car once I hit that rock at 200 miles an hour? What's likely going to happen? I'm likely going to crash. Think about that with reactivity. The more reactive something is, the harder it is for us to control. And remember, in the lab, we're trying to use nature to make reactions occur that we want, while still being able to control the products that we form and not get byproducts. So in this case, our reactivity of fluorine is just too reactive, so we won't ever use it, because it's just going to, give us a bunch of byproducts, multiple fluorinations, but also it's hard to work with in this violent. So not really very useful. So of course, iodine is not product favored. We're not going to use iodine for this particular reaction. And fluorination is impractical. It's so exothermic that it's dangerous. So only chlorine and bromine is practical for use. If we break down our propagation steps to look at chlorine and bromination in more detail, we don't need to look at the other ones. We already talked about these. We can learn more about these reactions. So here we're forming our radical. And the radical we form of course, is the difference between our chlorine and our bromine radical. So what we see for chlorination, we get a negative 21 value for this first step, whereas for bromination, it's positive, meaning the first step in this reaction to get our intermediate is going to be exothermic for chlorination, but actually endothermic for bromination. And we'll see that this is actually going to be a really useful thing for us with bromination. Now remember, the overall reaction is going to be negative. Now our second propagation step is negative for both and about similar. So our difference is really here in this first step. And the real difference is we're looking at the fact that our halogen is, chlorine is stabilizing that halogen a bit more. So with this step, we don't have much of a difference. That's our last step. But what we see overall, our net reaction, they're both negative, but this one's going to be more negative. This particular step, we're going to look at in a lot of detail for selectivity. So chlorination is more product favored than bromination, but if we look at our reaction coordinate diagrams, what this shows is, because the first step for bromination is positive, our first step is exothermic, meaning our starting material is lower energy than our intermediate. If we look at chlorination, our starting material is actually higher in energy than our intermediate. And why is that? Again, looking at our propagation steps, what that's saying is that this is higher in energy than what results here. And for bromination, that's opposite. So both steps are exothermic. So bromination is going to occur more slowly, but that's not necessarily a bad thing, because it still can occur in a amount of time that's useful. Sometimes, if a reaction occurs too slowly, it's not useful. But in this case, it's going to occur fast enough to be useful, but slow enough to where we can control it. And both of them are overall exothermic, so they're both product favored. So we're going to look at how that makes bromination more useful. And the way that makes bromination more useful is in our regiochemistry. So for our regiochemistry, first off, we need a hydrogen on our carbon. We can't form a radical on our carbon if we don't have a hydrogen to extract. So as long as we have a hydrogen, we can get extraction. Just based on statistics, for our different possible products, these are our two possible regiochemistry products for this compound. Just statistic-wise, you think we might form the second one more because we have more hydrogen atoms that are available to extract. But what we actually see by observation is that we form this as our major product. But we'll still form a good bit of this, and that's going to be our problem with chlorination. And we're going to form all mono substitutions. But we form more of our more substituted chlorination. That makes sense because remember, our intermediate is a radical, and our most substituted radical is more stable. So it makes sense that leads to our major product, just based on that. So we'll form more of our secondary radical, but the big thing I want you to notice is there's not a lot of difference in activation energy between forming this and this radical, which means we can easily form both. We'll form more of this one because it's lower in energy, but we'll form both, and it'll be hard to separate them. Also, that means that if what we're trying to get is this compound, we're not going to get it in a very high yield because we're still making this compound. And the more carbon-hydrogen, distinct carbon-hydrogen bonds you have to form the same products, the lower your overall yield is going to be, because you're going to form all monohalogenated products. Now, if we look at bromination, in contrast, we're still going to form the more substituted bromination, but we get it in a very high yield, and we get almost none of these substituted. And this is why bromination is more useful. We don't have to worry about separating out this. We don't have a lot. We don't have to worry about our yield being affected. We're still going to have a pretty high yield of our more substituted. Now, we're always going to form the most substituted no matter which of the two examples that's major. But for our bromination, and if we play around with our conditions, we can get this down to 0. So our bromination, we can use conditions to only form our most substituted bromination. So why does it favor it so much more than chlorination does? And the key is the fact that the first step for bromination is endothermic. That's really where it keeps. So to really explain this, let's review a little bit. So first off, remember when we're talking about a kinetic product, we're talking about which product has a lower activation energy. When we're talking about thermodynamics, we're referring to our equilibrium concentrations of our reactants versus products. In other words, which product is lower in energy? Because we're assuming we're starting with the same reactants that form different possible products. So that's our review there. Our other review is Hammond's postulate. Hammond's postulate is really important that we understand before we go on. So, in Hammond's postulate, so in Hammond's postulate, remember what that states. That states that our transition state is going to look more like either the reactant or product. In this case, we're looking at the reactant versus intermediate. This is closer to an energy. And this is going to really matter. So if we're trying to figure out what the transition state looks between these two, the transition state for chlorination looks more like the reactants, versus the transition state for bromination looks more like the intermediate. Now the question is, what does the reactant and what does the intermediate look like? Because this is really what's bringing about our difference in selectivity. So in chlorination, our rate determining step transition state looks more like the reactants. In the reactants, because we're looking at this step, that was supposed to be a plus. I don't know why I put an H. In our reactants, our carbon-hydrogen bond is intact. And our products, we have a carbon radical. So if in chlorination, our transition state looks more like our reactant, that means our transition state looks more like the carbon-hydrogen bond still being a bond. But in transition, our bromination looks more like the radical. So we have our carbon-hydrogen bond more broken, and that looks more like the radical. So what we're really comparing is how much the radical stability affects our transition state. If this one looks less like a radical and more like the carbon-hydrogen bond, will the radical stability affect the transition state as much? It doesn't look like a radical as much, so will it affect the transition state, depending on if it's a primary, secondary, or tertiary radical? No, it doesn't have as much radical character. But in this one, it's really starting to look like a radical. So our transition state is going to be a lot affected by how stable the radical is going to be. So remember, this energy has to do with what this looks like. We can't ever isolate that. It's as the reaction's occurring. And that's where we see our difference. Our chlorination only has a small amount of radical character, so we don't see a very big difference between our transition states between a primary, secondary, or tertiary radical. Versus the bromination has a significant radical character, so we see a big difference in the transition state energies if it's a primary, secondary, or tertiary radical. Let's look at that based on our diagram. In chlorination, notice that in all cases, we're somewhat forming radical character. So in all cases, tertiary is going to be lower than secondary and primary. But if we look at our chlorination, the difference between our transition states is not very large, which means that at any given temperature we're using, it would be really hard to not go over all three transition states. So that means you're going to get all three products. You'll get less of this one, but that's still going to take away from how much tertiary, and you're going to have to separate it. But with halogenation, because our transition state looks more like the forming radical, we get a big difference in energy between the three stable radicals. And that means that depending on our reaction conditions, we can just get our compound to go over our lower transition state and not over our higher transition states. And that's why our bromination is more selective. So in the lab, bromination is typically more useful because it's more selective. And we see that with our difference in our yields. What you'll notice in our selectivity is fluorination is the least selective. Primary, secondary, tertiary, you get a pretty much equal amount of all of them. And remember, we said fluorination was the most reactive and not very useful in the lab because it's so reactive. We have some distinction between primary, secondary, and tertiary in chlorination, but in bromination we get the most distinction. And this is a key point throughout almost all of organic chemistry that you see, is that reactants that are less reactive generally are more selective. And we'll see that throughout this class. We'll talk about reagents and what things they'll react with. And oftentimes you'll see we'll use this reagent, it's more reactive, but it's going to react with everything. This reagent is less reactive, but it's only going to react with this one thing. So you get selectivity. And knowing selectivity and understanding that helps you to not get byproducts, helps you to get more of your desired product. It's basically using what you know to apply it to synthesis, which is what an organic chemist does. If you're making a new drug, you don't want to react in a position that's necessary for the drug to work. So you have to be good at doing this and choosing reagents that will react where you want it to and not where you don't. Sometimes it's impossible and you have to do other things like protect groups, and we'll also talk about that. And sometimes it is possible. So we're going to talk about selectivity a lot. And the big thing to remember is things that are less reactive, it's easier to control. So it's more selective. It still has to be reactive enough because iodine isn't reactive at all. We won't form products, so there's no control there. So it needs to be reactive, but it can be less reactive and be more useful. And that's what we see as bromination is more useful. So if we're drawing our product for this example, here we have Br2. H2 is just like, or you might say the triangle for heat. They both will have our radicals formed. This carbon, we can't get halogenation there. We don't have a hydrogen. We can't get our CH3 abstraction. That's too high in energy. So we won't get any reaction there. Then we have some primary positions, a secondary position, and a tertiary position. So our product is going to be the bromination at the tertiary position. Notice we have the same amount of carbons. The difference is we had a hydrogen abstraction at that tertiary position, forming the most stable possible radical. Now, if we were talking about chlorination, that would still be our major product, but we get products of the chlorination occurring here, 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 and here, which distinctly would be 1, 2, 3, 4 different products. We haven't talked about stereochemistry yet. So big mess with chlorination. Bromination, much more clean of a reaction. So if we look at this one, which I gave you last time, our answer is going to be in our tertiary position. That's going to be our product. If we look at this case again, oops, I don't have things. Again, this position doesn't have any hydrogens, so no reaction is going to happen. Remember, our deprotonation at an sp2 carbon, our hydrogen abstraction, is very slow because that radical is not stabilized at all. So allylic position, great, but our allylic position doesn't have a hydrogen. We're going to talk about allylic bromination soon. There's no hydrogen here, and we won't get a hydrogen abstraction on an sp2 carbon because that doesn't stabilize the radical. Go back at the bottom association energies from the beginning of the chapter. That's even less stable than our primary radical. And then we have primary. We'll form primary radical if we have a hydrogen abstraction in these places. We have secondary. And then, of course, we have one tertiary position, so that's where our bromination will occur. And again, at this point, we haven't talked about our stereochemistry, what we do. Also, you might think the Br2 will react with this double bond, and it could to get that addition reaction. So we're going to talk about ways to avoid that in the next couple of slides. Because that is a problem. Br2 will react with a pi bond in our addition reaction to do bromine and bromine. So that is true, and in that case you will get some of that product. We're going to talk about whenever we have a pi bond present, a better reagent to use in Br2. Go forward. So now we got to talk about stereochemistry. Big thing to remember here is, for stereochemistry, what's the geometry of the radical? If we form a radical in our halogen, if we form a stereocenter in our halogen, notice we know stereocenters. This is not a stereocenter, but we do form the stereocenter. The question is, what stereochemistry will we get? And the answer is we're going to get a racemic mixture. Because just like our carbocation, we can consider our radical to be that trigonoplanar or this fast interconversion. Either way, whichever side we abstract the hydrogen from, that's the side we're going to get our chlorination. And there's no reason for one face or the other to react more. So, once we form that radical, we can get the chlorination occurring on either side, which means we're going to form the racemic mixture. So just like anytime we went through a carbocation, we formed the racemic mixture. Anytime we go through a radical, if we form a stereocenter, we're going to form both products in about equal amount. So racemic mixture. Looking at this example, again, we're going to have all the mono-substituted products here. The first product, our major product, our most substituted is not a stereocenter. We have two CH3 groups. But this possibility is a stereocenter. And when we have this chlorine add, we no longer have a stereocenter here, but it makes this be a stereocenter. And there's no reason, again, why the chlorination would add on one side more than the other. So that means we get these two enantiomers. And then, of course, this one, which we don't have a stereocenter anymore. So this again shows how unuseful chlorination is. And this is just our monochlorinated product. Remember, multiple halide chlorination is hard to stop. So we'll also probably get some products where some compounds have multiple chlorines on them, and not just one. Chlorination is not very useful typically. With our bromination, we'd only get that first product. Now what if we start with a stereocenter? What will we get? We're still going to get the racemic mixture because the intermediate is still a trigonoplanar radical. So just like if we started with a stereocenter and we formed the carbocation, we'd get both racemic mixtures. If we start with a stereocenter and we get this, we're going to get both. If our reactive center started out as a stereocenter. So let's look at this example. We have Br2 and light. This is one of our products. And notice we're going to form both in enantiomers. And of course, our other product, I don't think I have it in here. It's going to be this one. And you're going to form both of those because this is tertiary, and so is this tertiary. So technically, this isn't a stereocenter. Let's change this a little bit so it is a stereocenter. Pretend like it had that. Okay, now it's a stereocenter. So even though bromination is more selective, if we have two tertiary positions, they're both going to react unless a stereos prevents it from reacting for some reason. And in this case, we would. So we would get both of these enantiomers, no matter what that stereocenter started out. Now here, we're not changing anything with this position, because that position isn't reacting. Remember, the stereocenter will be retained if we're not reacting in that position. So in this case, that stays the same. You do have to be careful when you're setting up these reactions. If you have two reactive positions that are pretty equal for reactivity, you're going to get reactivity in both cases. Oh. I don't know why it does that sometimes. Electronics are so weird. They're really nice when they do what you want them to. Okay. So looking back at this one, of course, our product's going to be our tertiary position, which is this one. But we're going to get both receiving mixtures, even though we started with a stereocenter to begin with. Because we're going to go through that trigonoplanar geometry. The last thing we're going to talk about today is allylic bromination. So looking at these three possible hydrogens, our lowest bond dissociation energy is going to be the hydrogen in blue. And it's going to be the hydrogen in blue because that radical is going to be allylic. It's in resonance with our double bond. And remember, that's going to be a more stable radical. So in the examples I showed before, there was no possibility of resonance, so our tertiary was the most stable. Here, resonance is going to stabilize more than primary, secondary, tertiary. Even if it's a primary allylic hydrogen, it's still going to stabilize more than a tertiary because it has that resonance. So that's going to be our most easily hydrogen to be abstracted because it forms our most stable radical. And if you look at our bond dissociation energies, you see that. The vanillic hydrogen, the one on the sp2 carbon, takes the most energy to break. Compared to these two secondaries, they're both secondary, but this one's lower in energy because it's stabilized by resonance. So with that being the case, that's going to be where our bromination is going to occur, wherever our most easily broken carbon-hydrogen bond is, whatever our most stable radical is. So this is called allylic halogenation, and we see it most with bromination because, again, it's more controlled than chlorination. Chlorination, you'll still get this, but then you'll get other byproducts as well. So when we have that pi bond, we'll get the bromination in the allylic position. Both of these are allylic, they're both equal, but you might have to consider which allylic position is more stable. There is a problem, and the main problem I alluded to in the example earlier is that when we have Br2 in a double bond, we can get addition. How do we avoid this? we can avoid this by not having a lot of Br2. So how do we do bromination without having a lot of Br2 present? Well, what we can do is use a reagent that releases the bromine radical but doesn't have Br2. So the most common is N-bromosuccinimide, which is NBS. NBS has a bond between nitrogen and bromide, and it's pretty easily broken. It has a pretty low bond association energy, and it releases a bromine radical in this radical. And this radical is stabilized by resonance and the fact that it's on that nitrogen. So we don't need a lot of NBS. We only need a very small amount, but it supplies bromine radical without having a Br2 bond. Now there's some chance that if you have too much bromine radical present, they can come together, form a Br2 bond, and then do an addition. So again, we don't need a lot of NBS. We don't need a lot of bromine radical present at any given time. So we have very small amounts of this NBS, but it releases a bromine radical without having Br2. So anytime you have a pi bond present, you want to use NBS. Technically, you could use NBS for any bromination. It wouldn't be wrong. But if you have a double bond present, you want to use NBS. You don't want to use Br2. Because you don't want this competing reaction. Even if you're using light. So heat or light initiates this, and again, you don't need a lot of it. Once you get that bromine radical, then you're going to get the allylic bromination, and you won't have to worry about addition reactions. So that's the key. So anytime you see a double bond present, it's better to use NBS. And you should know the terminology NBS. But if you know what this looks like, it makes sense. It just releases a bromine radical without having Br2 present. So once our bromine radical is present, we get the same reaction we've been seeing, forming the most stable radical, being allylic. And then, again, some bromine radical might form, or it might, that would be in our propagation step. Or it might just take it directly from the NBS, and we'll get this allylic bromination. And again, we won't have a lot of NBS. So some Br2 might reduce, but it's not going to be enough to do the addition reaction. So that's going to be really, really key. It's a minimal amount of Br2 is in the reaction. So you don't want to use Br2 when you have a double bond present. If we look at this one, if it's an asymmetric double bond, you have to be careful because you're likely going to form these two products. So looking at this one, the question is why? But let's look at our intermediate radical. Our intermediate radical, when we first have our hydrogen abstraction, is this one, but it has this resonance structure. And in the transition state, both can be captured. Because remember, this isn't going back and forth. This is saying that this carbon and this carbon are radical characters. Likely, this one will be in a little bit more, but for now, if I ask you to draw the products of the allylic bromination, I expect to see both of these. So I want you to recognize. Now, the examples I showed before were symmetric, so it didn't matter. So you have to consider that. And that is an issue. Neither of these formed a stereocenter, but just like before, if you form a stereocenter, you're going to get both in antimeres. So looking at this example, our major product will be this one, and minor products aren't being shown, but there are some you would likely form this product as well. Ooh, and that's a stereocenter. So we're going to talk about synthetic utility on Friday, and we're also going to really get into HBr and peroxide and look at that mechanism to understand why it's anti-Markovnikov. Remember, there is that talk today. It's in the culinary building. I don't know where. I've never been in the culinary building, but it's in there. So if you're interested in physics, I'm sure it'll be an interesting talk.